Good, let's start the class today. So we are going today to see the chapter 5 pictures and just discuss what we didn't discuss yet. There are probably a few topics. Let's start from this one. This is a very important picture because this one is showing how the function 1 over r, 1 over r squared, 1 over r cubed and 1 over r6 is changing with r. I mean, this is nothing unusual for any of you, but the important thing is that all of them are large for the small r, which is obvious. But for the large r, some of them are virtually zero. But some of them are non-zero for very, very, very long time. So, what it really means, it means that two ions are interacting with each other even if they are very far from each other. The ion and the dipole are going to interact with each other when they are not going to be maybe a bit farther, but for large distance the interaction is really zero. Two dipoles interaction is dying even faster, and the induced dipole or London forces is really dying fast. So the molecules have to be really close to each other to have this interaction. This is one of the reasons why in the gas phase these interactions are not so important, but in the liquid phase they are becoming really important. And this is the energy of such interactions, typical energy. This is not every energy, typical energy. So the most energetic interaction is the ion-ion type of interactions. You see around 250 units, whatever the units are. The ion dipole, still quite large. But all the others are relatively small effects and of similar size, except for the hydrogen bond, which can be strong. Good. These properties, these different forces between molecules, they can explain some of the effects. Let's take, for example, the noble gases, starting from helium and finishing at xenon. You see that the melting point of them is going up, 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 and up. And the reason for this is that the forces between these atoms are usually the London forces. Okay? Now, the London forces are larger when the molecule has more electrons, or maybe in other words, when the electrons are softer. What does it mean, soft electron? This sounds strange. But soft electrons usually means that that's the electron that doesn't fill the nucleus very well. And for the xenon, which has the 5s electrons, the 5s electrons are very far from the nucleus on average, comparing to helium when the electrons are very close to the nucleus. That's why the London forces are pretty large for xenon and pretty small for helium. And they are able to keep the atoms together in the solid up to this degree, up to the minus 112 Celsius, which is relatively large temperature. Similar story goes to boiling temperatures. These forces are able to keep the atoms in liquid before shooting them to the space into gas, again with a similar trend. You see that it's not only about atoms. The same story goes to molecules too. You see that larger molecule we go, the temperature of melting and temperature of boiling goes up. But of course, there wouldn't be a rule if there are no exceptions, like in chemistry always. So we have similar rule here, minus 14, 89, 51, but hydrogen fluoride is different. Why? Yeah, that's the only molecule on the list able to do hydrogen bonds. So not only the London forces are keeping them together, here also the hydrogen bonds are keeping them together. As you see, this is similar order of magnitude like HBr, HF. And here it's much larger than any others. Okay? So these are strong forces, these hydrogen bond forces, comparing to the other London forces, of course. Let's go further. More complicated molecules. Well, I don't know. No comments. Good. Another thing. The London forces, or the induced dipole forces, are they largest for the round molecules, or a long molecules, or a flat molecules? And this is answer to this question. If two molecules are round, like this, and there is the induced dipole, induced positive charge, induced negative charge located here, induced negative, induced positive, you see that positive and negative are relatively close to each other. But the other positive and the other negative are very far. So the effective force between these two is large, but effective force between these two is very small. When you have a long molecule and you have the induced dipoles in this form, you can get short distance between induced charges and short distance between the induced charges. So in this case we have two short, strong interactions between induced charges. So the thing to remember is for the long molecules or flat molecules, their overlapping is better than for balls. That's why usually the London forces are larger for something what is long than something what is short. This is usually a typical question at the final term. They give you two different isomers. For example, something what looks like that, and something what looks like that. You can count, they have the same total formula. 5 carbons, 12 hydrogens, but these one are more similar to the ball, to this case. These one are longer, they are more similar to this case. So these interact in the liquid better than the interaction between these molecules. So you can expect that the boiling point of this one will be higher because more forces. And the boiling point of this one will be lower. I don't speak about room temperature, thank you, but for some low temperatures when minus, I don't know, minus 50? When it's liquid. Good. Let's go further. Forget about this part. Now we are discussing this part. So, okay, in this part, what we are discussing, you have very nice thing. You go to the next period, more and more electrons and molecules that kind of are the same. H2S, H2SE, H2T. So what we are doing, we are going to the periodic table of elements. H2O, H2S, H2SE, H2T. H3N, PH3, SH3, SBH3, and so on. So go down. If you go down with in the periodic table of elements, it means that you have more and more electrons, and finally, the London forces are larger and larger. Finally, the boiling temperature goes up and up. So we are going up, 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 up for all of them. The same trend, easy to understand. But something strange happens here. It doesn't happen for CH4. CH4 is exactly as we predicted, but it happened for NH3, HF, and H2O. And again, these are the hydrogen bonds. These three molecules, they can make hydrogen bonds, and these extra hydrogen forces, hydrogen bond forces, are strong enough to change the boiling point outside of these lines. Next thing that we didn't discuss yet. If you have a bottle with oil and you have a bottle with water and you mix them, you see that the water is moving fast, but the oil is kind of moving slowly. Okay? The property, the physical property that decides about if liquid is moving fast or slow is called viscosity. And this plot is showing which liquids have large viscosity and which of them has small viscosity. You see that one of the largest viscosities is the mercury, the metal, liquid metal. The smallest one on this plot is the ether. And water is somewhere here. Water has hydrogen bond, and when water wants to move, water molecule wants to move, it has to break the hydrogen bonds on the way. That's why it's pretty high on this list. Ethanol, similarly, that has hydrogen bonds that doesn't let it flow well. So you can think how such a flow looks like, and this is a picture showing how the flow of liquid molecule looks like. If they are balls, they can flow very nicely to each other, but when they are long molecules, like this one, you can expect that sometimes they are bent like that, and they cannot flow very easily. So usually very long molecules cannot flow very nicely and have high viscosity. And this is a picture showing this. Another property of liquids is something called surface tension. Well, surface tension is something easy to understand. Each of these molecules is interacting with this, with this, with this, with this, and with this. The average number of interaction inside is maybe, I don't know, 10, maybe 12, 20. But if you go to the surface, you see that there is nothing to interact here. So the energy is smaller. And the molecules don't want to be on the surface. The molecules want to go inside. So every normal molecule wants to be inside. And none of them wants to be outside. What it means? It means that every liquid tries to have as high volume as possible and as small surface as possible. What is the shape with the smallest surface and with the largest volume at the same time? Sphere, yes, exactly. And that's why when you have water molecules, they have the shape of the sphere because they have minimal surface. Well, these spheres are not ideal spheres, and the reason for that is that the gravitation makes them a bit longer this direction than this direction. But almost ideal spheres, which is a very nice picture showing this. Okay. This force kicking them inside is called surface tension. And how do you understand this? Let's try to put something inside. Then you have to separate the molecules from each other. If it's easy to separate them from each other and put something inside, the surface tension is small. But when it's very difficult to enter, the surface tension is opposite, it's high. Good. Let's go further. What is the surface tension? Again, you see that the record holder probably for liquid would be mercury. Extremely high. And as you probably know, in the old Arabic fairy tales, there was always a swimming pool full of mercury. The kings had a swimming pool full of mercury. They had a rock on the top, and they were walking on the rock, on the liquids. That was one of the high-level people. Unfortunately, they didn't know it's very poisonous, so they didn't live very long. Well, there's always price and penalty for everything in life. Good. So mercury has one of the highest surface tension. It's very difficult to enter. You know that if you put a rock on the water, you would go down. And the reason for that is here. 472 to 72. Much smaller surface tension. Good. A small surface tension. You see that hexane, benzene has very small surface tension. Good. Let's go further. Next thing. How many people know why this one is down, why this one is up? Hand up. 1. 2. Okay. Good. I mean, nice. If you have a box with liquid inside, 2 molecules of liquid are sticking to each other because of the London forces. This force is called cohesion. Now, every liquid molecule is also sticking to the box. There's also some atoms here in the box. This force is called adhesion. Okay. Now, they can be exactly the same. If these 2 forces is exactly the same, then if you take very tall pipe and put the liquid inside, then this level would be exactly the same. This is the cohesion forces are equal to the adhesion forces. There is no meniscus, it's flat. But now it may happen that the cohesion forces are larger than the adhesion forces. What it means? It means that molecules prefer to be next to each other than next to the box. Well, if this is the case, then the molecules try to minimize the surface contact. It should be somewhere here, but now we are gaining this part of surface contact, and molecules prefer to stay together inside. So when these forces are larger, then this shape is modified, or maybe I'll write it in a bit larger form. So this is the original one. The shape is modified. Everybody escapes from the surface, but everybody goes to the inside. Because it's better, the forces, the interaction are larger within the liquid. But there can be the other case. It can be the other case where you have forces of adhesion larger than the forces of cohesion. Then the original case was like that, but now everybody wants to go to the surface, so they have to climb to each other, and finally some of them are missing in the middle. And then you have the other shape, concave shape, and here you have the convex shape. Is it clear? I explain some more. I think it's clear. Let's go further. We know that crystal is a nice collection of atoms, and they are located in the surfaces, and the best thing to see it when you break a crystal. Then you see the so-called faces of the crystal. And now somebody would tell, but this is strange. This face, I understand, would be this, but why this one is at the strange angle? It's for the reason that the crystallization was done not in a very nice way. At the beginning, when the liquid was becoming crystal, it started in 2 different places. And this one started growing that direction, but this one started growing this direction. So finally, when they met, you can see this angle, for example, between these 2 walls, this wall and this wall. Good, let's go further. Here you have a difference between SiO2, so a usual sand in a regular crystal, and disordered crystal. This one on this picture is not so much different than this. But if you see that when this crystal gets very nicely organized that way, then you see the faces of the crystal. One face is here, another face is here, another face is here. Very beautiful. For the glass, you never see it. But the question is, really? You never see the crystal structure for the glass? And the answer is, yes, you see the crystal structure for the glass, but the problem is that coming from here to here takes a long time. And if you get a normal glass and keep it for a long time, you get this one. What is long time? Decades. Longer. 500, 600 years. And that's another reason why in Europe, when you have many old churches, it's very difficult to find old window. Because this one is very elastic. When the wind is blowing, nothing happens. Well, I hope nothing will happen. Nothing happens, it doesn't break. But when it's becoming a crystal, and it has crystal structure, it's very easy to break it if it's thin. So there are two reasons. One of them, we know that structures of this type, they can flow like liquids. They are kind of frozen liquids. Second thing is they crystallize. So the flowing down of such glass would change the shape. The final shape would be very thin here and would be getting larger down. That's the first thing. Second thing, it starts crystallizing. It starts having these crystal structures which is very easy to break. So there are two reasons why the glass is so unstable with years. Good. Next. Many people are saying that on this picture we can see the surface. I guess this one would be copper or nickel. Okay, you take a metal, whatever it is, you sit with a tissue and you go like that for 2 years maybe. After you do it for 2 years, the surface of the metal becomes really smooth. Really smooth. When I say really smooth, I mean the atoms are really at the same level, all of them. In a usual thing, you have next layer of atoms, next layer of atom. Here, after doing for 2 years this to the metal, it's really flat. And then you can make a picture like that. So many people believe that these actually are atoms. How this picture was made? This is called scanning tunneling microscopy. And you start by making a tip. What is a tip? You take a wire and you cut like that. And you cut on the other side. Well, somebody says it would be very difficult because the wire from here to here is maybe, I don't know, 10 to 9 atoms. There's a huge number of atoms there. If you cut it like that, maybe this part would have, if you are lucky, 10 to the third atoms. That's true, that's true. If you are using normal knife and normal scissors, that's probably true. But if you are using laser techniques, people are able to do wire with only one atom at the end. Single atom like that. They are able to do this. This doesn't last for long. You have to replace them very often. Because this one atom is very often broken, some of them are gone. But people are able to do this. Then they put a current to this. And they take the surface, which is usually a metal, and put a negative current there. Okay? Now, they put a battery between them, and they put the amperometer between them to measure the current, like that. And what they do, they go down. If they are separated, there is no current. This is showing 0. But when they get closer to each other, finally there is a distance, when they will be very close, when the current starts flowing between these two surfaces. And they get some current. Now what they do, they start shifting it right, then go to the end, come back, come back, come back, and do like that for hours. And that's exactly what you are getting. This is the image of the surface by amperometer. This one is showing how much current is flowing at different positions of this tip. And you see that at some places there is a lot of current, but at some places not so much. Now, there is a lot of talking what this picture really showing. Some people say they are showing atoms. Well, I don't believe this. You don't see atoms by amperometer, by the current. Probably what these pictures are really showing is the density of orbitals. Because the electron current is an electron coming from orbital to orbital in a simplified picture. So you see that in this place there are many orbitals when the electron can come, and in this place not so many. But somebody else says, well, if orbitals, they must be on atoms. So in this sense we really see atoms. Yes, that is probably a true picture. Why this is useful, except of making this nice colorful picture? Of course, I don't have to tell you that you don't see these colors. What you see is just 0, 1, 2, 3, 4. This is just made very nice later to publish it nicely. Good. What you really see, how it is used, except of making this nice picture and showing the surface. You can ask questions. For example, one of the questions was asked here. They took the sodium iodide. Let me make sure if this was sodium iodide or something else. Sodium iodide, yes. They took this crystal and they put it on copper. They had very nice copper surface, and on the top of the copper they put this sodium iodide, equally spacing, and they let it go. Turned out that after some time the surface was empty again, and all the sodium iodide condensate in one place. 1, 2, 3. They don't like to be two-dimensional structures. They like to be three-dimensional structures. This is clearly showing that the cohesion inside this crystal is larger than the adhesion to the copper. Still, it's useful study. Let's continue. Different types of solids. Oh, sorry, I got in your back. Okay, you have a present for me. Okay, let's continue. Different types of solids. We said they are already metallic, ionic, network, and molecular. Here you have the examples of them. Metallic, nothing to talk, just metals. For ionics, you probably know many of them. The network one. Turns out that many elements like carbon or boron or phosphorus, they are making this type of network crystals, but also many real molecules. Then when you say that sand is SiO2, is it really true? Not really. The real truth about sand is that this is really SiNO2N. And when you are in high school, they are teaching you about V5O2. Is it opposite? Yeah. V2O5. About catalyzer, the real truth about this is these are very large numbers. This is just not a simple molecule. They are just coming in the crystal. Good. Let's continue. Closed packed structures. They are everywhere. I guess in Taiwan especially they are everywhere because they are selling fruits in many places. But, by the way, is it easy to say if they are hexagonal closed pack or cubic closed pack? For me, not so easy. But let's see the next pictures, which are possibly showing how to distinguish between them. We said that the layer A and layer B are always the same. There is never a difference. There is only one way of putting them. But we see that the next layer, we can put the atom here, or we can put the atom here. And these two places are different. And that's exactly what is done in the next two things. You can first put the next atom exactly above this one under, the blue one. So we see that the blue one is exactly above the blue one under. And you see that these spaces are visible for a long, long time. If you do this, the single cell will look like that. And we already said it's a hexagonal structure and hexagonal closed packed structure, and this picture I think is convincing why it is like that. These drawings are better than my drawings, so you better stick to them. Good. If you don't do what we did just a few moments ago, put this atom above the previous atom, but if we put it in this position, then we get the cubic closed packed structure, and you see that the atoms are kind of like shifting up, up. The next one will be here, the next one will be there, and so on and so on. And here you don't see any holes if you look through this structure. And the cubic cell, again, this is better than what I was showing. You see that red one is the top. Then the green and green is in the middle of the wall. Middle of this wall, middle of this wall, and the middle of this wall. Then you have the I skip this. I don't want to say anymore. Good. The tetrahedral holes and octahedral holes. I was drawing them on the blackboard, and here you can see them in the reality. This one, tetrahedral, has one atom down and three atoms up. That's why you get these tetrahedral holes. This one, octahedral one, has three atoms up and three atoms down, making this octahedral shape like that. Where is the octahedral? You see that this red atom connected here makes the bipyramid shape of the octahedral. These are much better than my drawing. I still have to practice a lot. Okay. Now, we said that there are only 14 Bravais types, but not more than 14. And this picture is kind of explaining why there are not more than 14. And you can draw it kind of easily on a surface. If you start with the smallest possible number of them, 3, it's very easy to imagine how to cover all the space with triangles. And so on and so on. I can cover all the space, no empty spaces between triangles. So triangles can cover all the space. Similarly, the cubes, no, not cubes, squares, you can cover all the space like that, no problem. This picture is showing that if you start with pentagons, it's impossible to cover all the space without making empty spaces. How much time we have? One minute? 4:30 we should finish. 10 minutes. Okay, let's continue. Just from my perspective, this looked like, yeah, like one. Okay. Okay, let's continue next picture. We are saying that if you take the CCP structure, or in other words, the cubic F unit cell, which is made by the green structures, and we put the cations as the red ones, then we get the sodium chloride structures. And here you have a nice example of this one. So it really looks like there is a primitive cube here with different corners, but in reality you see that it is the closed pack cubic structure, or other way of saying it will be cubic F structure for green atoms and cubic F structure for the red atoms. The other type, this is the sodium chloride. The other type is the cesium chloride. You can see that one atom is inside and the other 8 are around. We're drawing it last time, but here just nice pictures, so I think it's nice to see them again. And the last type, the difficult one, we said that the anion make again the cubic F cell, and now you can say that every big cell is divided into these 8 small cells. Now 8 small cells have centers. Now half of them is occupied, half of them is empty. So you see the dark blue are the occupied cells, and each of them has inside the zinc cation. The other 8, this one, this one, this one, and this one, they are empty. Oh, no, this one. They are empty. They have nothing inside. And this is the zinc blend structure. Let's go further. This is an interesting thing. I kind of like this plot because it's showing how the density is changing with the temperature. And the interesting part is that you have the freezing point here and you have the freezing point here. Turns out that after freezing, the volume of solid can go down, can go up, or can go down. Yes. The density goes up, so the volume must go opposite direction. And why it's happening? Usually this is the case. When you have a solid is taking less space than liquid. It makes sense. If there is a very nice order, then it's very difficult to put something between. In the water molecule, when everything is moving all the time, very often there are large spaces between molecules in the liquid phase. So we can expect that the solid should have smaller volume than the liquid. And if the volume is smaller, the density would be higher, the same mass. But for water it's opposite. Turns out that around this temperature in 0, the density drops down. And the reason for that is that in water, in the liquid water, the number of hydrogen bonds is not perfect. It means not every molecule has 2 hydrogen bonds. But in ice, yes, every molecule has 2 hydrogen bonds. So if this bond, they require some distance between molecules. In the liquid water, the distance can be smaller because not all of them are bounded by the hydrogen bond. That's why by freezing, finally the volume is larger. This is a very unusual thing and happens not for many liquids. Here you have the effect. Ice has higher density and is floating. In this case, this is the tetrachloromethane, and the frozen tetrachloromethane goes down and the liquid is on the top. Notice that this one has very high impact on the life on the surface of the Earth. If water wouldn't be like that, but like that, it means that no sea, no river, no lake would be ever frozen. It means also that probably no people would live in the United States by maybe 200 years ago even. Because the first people who crossed to America were from Asia and they just crossed on the frozen sea to Alaska. And probably if this wouldn't happen, there wouldn't be Native Americans there. So these are interesting things. They have quite of interesting connotations in the real life. Okay, Now we are going to discuss two types of the network crystals. Both of them are carbons. First of them is the diamond. How the diamond is made? Well, every carbon atom is connected to 4 another carbons. 3 of them up, 1 of them down. Now this one has 1 up, 3 of them down. So you can consider this as the following connection: carbon, carbon, in the plane, sticking out, behind, sticking out, behind. And if you follow doing this, you find the crystal structure of diamond. The other one, graphite, is not so nice. You see first that you have these 6-member rings of carbon continued in this direction and continued in this direction. So you have a very nice structure that looks like that. 6, 6, 6, 6, 6, and so on, in 2 dimensions. Only in 2 dimensions. In the third dimension, there is relatively large separation between layers. So you have here layer A, layer B, and then layer C again. They say layer A because they just overlap with the layer A. So you see that every second layer is shifted. So this is the structure of graphite, and if you look at this and you see this very big separation between layers, you probably know that graphite wouldn't be so strong as the diamond is. And this is the truth. Diamond is one of the strongest surfaces of crystals in the world, but graphite is relatively easy to break. And one of the reasons why you can use your pencils is this property of graphite, that if you write down, one surface is staying on the paper, but the other is still in your pencil. They're just sliding on each other. So this is how it's used for making pencils. Go further. We discussed 2 different types of alloys. One was the substitutional alloys, and you see here such an alloy with 2 different types of atoms. Let's say there will be copper and there will be gold or silver. And you see that if they have the same size, then the crystal structure is almost perfect. Just some of them are replaced by the other atom, but they have similar size, so the crystal doesn't really know about this. There is the other case, when they are really small, the other atoms, then maybe they can enter in these holes. And this is exactly in the interstitial alloys, when the other atoms, much smaller, enter the holes. You see 2 things. First thing is that to enter this hole, these atoms have to be separated. These holes, in the original case, are too small to put anything there. So we have to push them away, like that. Aha, that's interesting, because this is probably showing that this one has very nice property of the crystal. It means it's very easy to break it, because it has very sharp surfaces. But in this case, opposite. This is difficult to break it, because if you see, this layer is not straight. So the surfaces of the crystal would be kind of folded, and it's easy to bend it. And that exactly happens. This type of interstitial alloys are very easy to model into different shapes. Last 4 pictures and we finish our class. This is one of the molecules. There is a liquid crystal. This molecule, when it's solid and is becoming liquid, it has this, I don't know, 5 or 10 degrees range when it's half melted and when it's becoming liquid crystal. It means that in this plane it can move, but it cannot rotate like that. So it can slide over each other that way. And the molecules can slide over each other that way. They can make different arrangements. And here you have the three different arrangements when these long molecules are kind of ordered in this direction and kind of disordered in this direction. In this case, they are ordered both directions. And in this case, you have the three-dimensional picture showing that this is ordered, but the order is different. Now this holospheric phase is very interesting one for a specific reason. Turns out that the angle between these two depends extremely much on temperature. If you change the temperature, but very small, tiny effect, this one going to turn. Somebody would say, what's the difference? There is a difference. And the reason is, if you have light going through such surface, in this case, all the light is going through. In this case, less light, zero light is going through. So something can be white or black depending on the temperature. And this is exactly what is used for the thermometers that you put to your forehead and check the color, blue, green, red, depending on the temperature. They have different level of orientation, and depending on the temperature of your forehead, I guess mine will be red today, they are showing different transmission of different colors of light and finally give you the color of the final thing. And that's the last picture. I said that some of the liquid crystals are made by the long molecules with different ends. And here you have perfect thing. This type of molecules have one name that everybody is using every day, and the name is soaps. Yeah, exactly. So maybe this one perfectly is not the soap we use, but generally it has one end that sticks to oils and another end that sticks to water, and it's used for washing our hands. Thank you.